Yeah, we'll do this. Okay. Yeah. Okay, so today's topic is topic 4 and 14, and that is bonding in the entirety of that, covering types of bonds, Lewis structures, Vesper shapes, hybridization in higher level, and formal charge in higher level. But the first thing I kind of want to do is do a good summary of the types of bonding. There's 3 types of bonding. And so what we want to do first is we want to subdivide a table into, let's see, we will do it as 4 parts here. So not sure exactly how long this is going to be, so don't necessarily draw like the end of it, but we have 3 major types of bonding that we're going to address: ionic, covalent, and metallic. We'll just call this description. So this allows us to kind of categorize how to describe each of these types of bondings when we're comparing them to each other. This is a really common multiple choice question. A lot of times they'll say, which of the statements best describes ionic bonding or covalent bonding or metallic bonding? And so the first thing we want to establish is the definition of each of them, okay? And every one of these definitions starts with the electrostatic attraction between. So we're gonna assume that each definition starts with electrostatic attraction between, and it's the species that it's between which makes up the difference between ionic, covalent, and metallic bonding. For ionic bonding, it is oppositely charged ions. You can say positive and negative. You can say like cations and anions, but as long as you're addressing the fact that they are oppositely charged. Okay. So that's how you define an ionic bond. A covalent bond is electrostatic attraction between a shared pair of electrons oops, um, positive nuclei. Okay, so shared pair of electrons and positively charged nuclei. Where metallic is between cations and delocalized electrons. Okay. So these are the differences between the 3 types of bonding that you're going to describe. Okay. So, no, Juan Diego, you're blocking like 5 people. You need to find a different seat. No, Juan Diego, they're not going to tell you. I'm telling you. Move the table. Okay. Okay. Sorry, video. I'm letting Juan Diego find a seat because he got here late, and so he can't find a good seat. Okay. We're not editing this out. I hope the people on YouTube are watching this. Yes, Sophia. I can't on this screen. I can't make it any bigger. Let me. Like for some reason, Zoom doesn't let me. I don't know if I can. Um, actually, maybe I can do this. Maybe I can get creative here. Maybe I can drag this. I don't think that's bigger though. Yeah, it's as big as I can make it. For some reason, Zoom doesn't let me kind of make it any bigger than that. I don't know if I can zoom in on it. Maybe I can. Hold on a second. Maybe I could do this. Maybe I can find a way to like. No, no, it's okay. Like it is kind of annoying because there's a lot of like. Maybe I can like zoom in or something like that. Hold on a second. Can I zoom? Oh no, this is super sensitive. No, I can't. Yeah, I don't think I can make it any bigger, unfortunately. Okay. Yes. Uh, I think the emphasis is on shared pair of electrons. So you can say, like, I think negatively charged electrons are redundant in this case. Yeah. All right. So the first thing is establishing a definition for these. Okay. I do. Let me do this. I will zoom in and kind of scroll across so that hopefully you can see a little better. Okay. The second thing is kind of a general illustration of that concept. And so with ionic bonding, you've essentially got this kind of structure of alternating ions that are attracted to each other, but they are independent of each other with a strong attraction between them.
Are you drawing something, Mr.
Yeah. Oh, can you not see it?
No.
Oh, goodness. Okay. So I guess, oh, hold on a second. I think because I shared it onto the screen, it didn't work. Hold on a second. You know what? I need to duplicate it. Yeah, I don't think we're going to be able to get around this. Let's see. I don't think it's any smaller over here, to be honest with you. Okay. So the ionic, you have these independent ions positively and negatively charged. With covalent, you kind of want to think of it as more of these positive nuclei sharing a pair of electrons in between them, and the attraction that the positive nuclei are both having for that pair of electrons that are between them is what causes that covalent bond. That's what you kind of want to imagine that's happening here. And so that attraction toward those negative electrons is what's creating a covalent bond here. Whereas in a metallic bond, you have these cations that are donating electrons to the surroundings, and then they're surrounded by these electrons. You do want to emphasize the term delocalized electrons. I know some textbooks will say sea of electrons and stuff like that, but the proper term is delocalized electrons. And so if you wanted to illustrate metallic bonding, that's really what metallic bonding is. And this is kind of why their properties vary across covalent, ionic, and metallic compounds because of how they're bonded. Questions so far? Okay. Oh, okay. We'll draw a line here. Okay. Bless you. Okay. Next thing. One of the some of the physical properties that we'll need to talk about here. One is melting point. Okay. And so melting point, you would categorize ionic as very high. We're talking about plus 1,000 like above 1,000 degrees Celsius for these ionic compounds. Okay. For metallic, you would say high, like maybe medium to high. So that's like in the hundreds of degrees Celsius, but not as high as ionic compounds. Covalent is kind of tricky because there's kind of two types of covalent molecules you have to worry about. Molecular covalent molecules that are like water or like CO2 or like um, ammonia have relatively low um, melting points. Water melts at 0 degrees Celsius, right? And so very low. But network covalent, like diamond and graphite, have very high um, melting points. So you do want to be careful about the differentiation between those types of covalent molecules. But yes, most molecules, independent molecules that aren't network covalently bonded, have very low melting points. Yes. It's because the attraction between the positive and negative are very, very strong, and the energy it takes to actually separate the ions far enough apart so that they don't attract each other is very, very high. So, like, I think the melting point of sodium chloride is about, I don't know, like 1,200 degrees Celsius. It is very high, medium to high. So you would rank it as in like ionic and network covalent, very high, and then below that metallic, and then way below that like molecular covalent compounds. This is kind of a common like multiple choice question. What they'll do is they'll describe a compound that has certain properties, and you'll be able to differentiate between the type of bonding based on those properties. So one thing they'll tell you is what the melting point is. Another thing they'll tell you is conductivity. Okay, when is it conductive? That will help you eliminate which one is which. And so, for example, metallic is always conductive. Okay, covalent are never, except for graphite, which is a network covalent. That's kind of one of the rare situations, but um, molecular compounds are generally not conductive. And ionic are only conductive when they're dissolved in water, liquid, or a gas. In their solid state, they do not conduct electricity. And that is a defining characteristic between a solid metallic compound versus a solid ionic compound, is that the ionic compound will not conduct electricity. So that's one of the descriptions that you can use to differentiate between them when they're unknown compounds. Sorry, my colors are all over everywhere. I don't have a method to my madness right now with the colors. I'm just trying to make it kind of stand out each row. Questions so far? I want to check something. Yes, except solid. Correct. Yeah. Yes. Yeah, yeah. The two circles with a positive charge are the nuclei of the two atoms that are bonded together. No, no, no. They're attracted to the pair of electrons in between them. So I'm just showing that's the electrostatic attraction. Whereas, like here, the electrostatic attraction is between the two ions, right? And the electrostatic attraction here is with the pair of the electrons delocalized around. Oh, yes, Nick. Correct. Yes. Yeah, we'll kind of keep it that way if there's a differentiation between those. Yes. Right, yeah. So conductivity, remember, requires like free moving electrons or ions. So ionic compounds have fixed ions in their solid state. So there's no mobility of electricity between those. So conductivity requires free moving electrons or ions. So if you're trying to explain conductivity in a short answer question, you want to establish that to have conductivity, the species needs to have free moving electrons or ions. So when you dissolve it in water, the water separates the ions apart. So therefore, there's electricity can pass through them. Let's see. We'll add in here. Um, Solubility in water. How well does it dissolve in water? Okay. Here you'll say most ionic compounds are soluble. Okay. There are some ionic compounds that are not soluble, but in the IB, you don't need to know solubility rules. So you will be told when a compound is not soluble in water. Okay. Most ionic compounds, especially group one compounds, group one metal compounds, are soluble in water. Okay. It's much more common for an ionic compound to be soluble in water than not. Because remember, water's polar, so it generally can attract the ions in an ionic compound and separate them apart. But sometimes the ionic attraction is so strong that the water can't overcome it. Here, those network covalents are not soluble, and here it depends on polarity. Because remember, likes dissolve likes. So similar molecular polarities dissolve similar molecular polarities. So if the molecule you're putting in water is polar, water will dissolve it or mix with it. If the molecule is nonpolar, it's not going to interact, and the nonpolar molecules are going to stay together, and the water molecules are going to stay together. That's why oil and water separate, because oil would rather be attracted to itself than the water that it's in. Yes, Sophia. Yes, correct. So diamonds don't conduct, fullerenes don't conduct, um, um, SiO2 doesn't conduct either. Okay. Oh, yes. Oh, Jada, and then yeah, go ahead, Amon. No, it's okay. Right, Jada. Right, because the general phrase, and it's not an official IB phrase, but the general phrase that books teach you is likes dissolve likes. So things that are similar in polarity will dissolve things in similar in polarity. So you need to know water is very polar. So it's going to seek out to mix with other polar species, but not mix with non-polar species. They would mix. Yes, correct. Yeah, that's how that's why like nail polish and acetone mix pretty well because acetone's pretty nonpolar. Nail polish is usually kind of oil based or something like that, so they dissolve each other very very well. And so, but that's why most of them are waterproof. They don't dissolve when you get wash your hands and stuff like that. Yes, on there you go. Yeah, so a network covalent is a structure where all of the atoms are in a giant network and they're all covalently bonded to each other, and there's not an individual molecule that you can take out of it. Like for diamond, you can't take a diamond molecule out of it. It's the entire structure as a whole. Whereas water, you can take a water molecule out of the sample because they're they're weakly attracted to each other. So diamond, graphite, fullerenes, SiO2. We'll talk about those examples in a little bit as well. Okay. Metallic is kind of tricky. I don't know if I would call it solubility, but like group 1 and group 2 are reactive in water. Most of the other ones don't really dissolve that much in water, but group 1 and group 2 metals are very reactive in water. They react with water to produce hydroxides and basic solutions. That's why they're called alkali metals and alkaline earth metals, because they make basic solutions. Yes, the alkali ones are obviously more reactive and they create more energy and much more explosive. Questions? Okay, 35. I was just doing a head count. It's 35. Okay. Um, we'll do here additional properties that you might want to kind of mention here. Okay. And then we'll talk about some examples, and we'll even put naming in this column as well. This chart is going to be very long, but good news is that encapsulates probably about a third of all the information you need to know for SL. Because really, SL is bonding, like ionic covalent metallic, and then it's the other third is Lewis structures, and the last third is IMFs. So like this table is kind of summarizing a third of the material you need to know for this unit. Okay, additional properties. Okay, ionic compounds are brittle. Okay, what I mean by brittle is that when you apply force to them, they shatter, break into little pieces. They don't break into, they aren't very malleable. They can't withstand a lot of force. Or even, but when they do break, they break up into uneven, like kind of smaller pieces. Okay. Covalent are also brittle. All of them are very brittle. Like even diamond, if you break a diamond, it shatters into smaller pieces, unequal pieces too. I'm trying to think if there's any other kind of big ones here. Metallic, there's a couple more terms you want to do. Malleable, being hammered into thin sheets. Ductile, which is being pulled into thin wires. And also luster. It has a like kind of a shine to it when it's not oxidized already. Yeah, like it can be kind of pulled into like thin threads and stuff like that. So wires, that's why copper wires are the way they are, because you can heat up copper and pull it into really thin strands and make it into wire. Yes, Asdean. Yes. That means that if you place it in water, it will not break down. It will stay in its entire state. Yes. Yeah. So like if you mix oil and water, because oil is very nonpolar, it'll just separate in its own layer away from the water, because it's actually rather attracted to itself than the water. Correct. Yeah. Okay. Yes. For the most part, yes. I think you can say that as a general trend for metals, yes. Okay. Um, sorry, I'm just gonna keep extending these lines. The next thing is um, what determines strength? Okay. So what we're talking about here is like if I'm comparing two ionic compounds, what do I look at to determine whether which one's stronger bond or not? So for ionic compounds, and this might be a little HL, but I still think it's important. It is the ions charges and the ionic radii. Okay. You want the ionic charge to be higher and the radii to be smaller, to be stronger. So if you look at two ionic compounds, you look at their charges first, and then if they're the same charge, then you look at the smaller ions. So you are applying that in here. So an ion that has a +2 charge has a stronger attraction than an ion that has a +1 charge. And a +2 and -2 is stronger than a +3 and a -1. It's the product of the charges that you're really looking at. Kind of relates a little bit back to physics. If you think about like Q1, Q2 over R squared, that kind of idea is kind of what applies to ionic like strength. So the charge of each times each other divided by the radii between them. So that you'll want to use to determine very common multiple choice question. They'll say, which of the following compounds has the strongest ionic bond? And so you look at all their charges. If all their charges are the same, then you look for the combination that is the smallest ionic radii. So that's a really common one. Yes. Oh, just the more positive, more negative, the greater the attraction between the species. Oh, Juan Diego and then Jada. Yes, correct. You want it smaller because you want them closer to each other. Like a higher charge but a larger radius also. No, you won't ever compare diagonally. So that's a good question. But the IB will make it so that there's one constant. You're only comparing one thing about them. I see what you're saying. Like, how do you compare something that has a +2 versus +1 if the +1's smaller than the +2? No, I would always go by charge first. And if there's no difference there, then go to radius. Don't try to do both of them at the same time. Jada. Okay. So do ionic charge first and then ionic radii second. Yes. Well, because for ionic traction, you want the atoms as close to each other as possible. And so you would want even the negative ions to be smaller so they could be closer packed together, which means greater attraction. Because the attraction weakens as they get further and further apart from each other. So it doesn't matter whether it's positive or negative. You just want them as close to each other as possible in their crystal lattice. Yeah. Okay. Yes. Oh no, it doesn't matter which one. Like what I would do one day ago is figure out the charge of each ion and multiply them together and just take the absolute value. So like a +2 and a -2 is a product of 4. And a +3 and a -1 is a product of 3. And a +1 and a -3 is a product of 3. So the 4 is greater than both threes. That's the way you want to treat it. So don't worry about the sign. It's just the quantity. Okay. For covalent molecules, for bonding, it is electronegativity. So the stronger the covalent bond, the greater the electronegativity difference between them. Okay. Now for molecular attraction, it's polarity slash IMF. And so if you're looking at just a single bond in a molecule, you compare the electronegativity differences. But if you're looking at two different covalent molecules like water versus methane, you would look at their polarity and their IMFs to see which one has a stronger attraction. Jada? Yeah, greater difference is stronger bond. Correct. Yes. Molecular attraction. Wait, where? Oh, I didn't split it up in half. I'm just writing it across the whole thing. Yeah. So I'm writing across the whole thing. Uh, okay. I thought I saw hands up, but that was false alarm. Okay. Okay. With metallic bonding, you go by the charge of the ion, charge of the cation, and then the radius, or ionic radius. And you want it to be smaller. Okay. Yes, Azim. Atoms, correct. Yeah, yeah, across molecules, correct. Okay. You want this to be larger. Oh, I can't make it any bigger. You want the charge of the cation to be larger and then the radii to be smaller. So if they ask you which metal has the strongest metallic bond, you would look at the larger charge, the most common charge of it, and if they're all tied, then the smaller one's better. And that affects all the properties as well. And if you're on the short answer, you can actually see this because one of the periodic tables has all the melting points and boiling points of the species. Because if you go here and you see this periodic table here, it's sideways. I'm sorry, but you can see that the melting point and boiling point both decrease. Melting points on the top, boiling points on the bottom. They decrease as you go down the same column. So notice that Li, Na, K, Rb, Cs, Fr all have positive one plus charge, but because Fr is bigger, the attraction with the delocalized electrons is smaller. And so that's reinforced with these values. And then also, if you notice, you go to 2 plus charge, it's significantly different. Like it's a drastic jump up when you go to the 2 plus column versus the 1 plus column. So this is kind of help you reinforce that concept as well in your data booklet. But remember, you don't get your data booklet on paper 1. So you do need to still know these concepts because they will, like if I'm the IB and I'm writing a question for multiple choice, I'm going to take advantage of stuff that you could find in the data booklet in the multiple choice because you don't have access to it. So they still want you to understand it. And so that's when you'll see a lot of multiple choice questions. Okay. Yes. Yes. Well, you would look at Na has the same radii. F is higher up on the periodic table, so it has a smaller radii. So NAF would have a stronger attraction. No. Well, actually, oh, no, not in that way. I see what you're saying, where one ion is larger and one smaller. No, I don't think they would do that. Usually what they do is they'll like have like NaCl, NAF, MgCl2, and then MgF2. So because you have Mg, you eliminate both NAs. And then between the MGs, you say, well, F is smaller, so MgF2 is the greatest one. So there will be an obvious like elimination that you can do. Okay, next row. I know lots of rows. Oops. Okay. Examples. Okay, just to kind of talk about a couple different examples here. And let's see. We'll put naming in here as well. Okay, we'll group this together so that way, because metallic doesn't really have any naming that you have to do, and so I'll put it in the same row here. So this one may be a little bit taller. So I'm going to give you a couple of variety of different examples of different ionic compounds with their names attached to them, so you can kind of make sure you observe the trend between them in the naming and stuff like that. So NaCl, oh, let me zoom in here, is sodium chloride. FeSO4 is iron 2 sulfate. This is ammonium fluoride. And this is zinc oxide. Zinc has a fixed oxidation number, so you don't need to write a Roman numeral. But this is where you see Roman numerals. The only time you see Roman numerals is in ionic bonding. That's the only time. There should never really be another time where you have Roman numerals except then. Now for covalent, you might have something like um, carbon tetrachloride or carbon dioxide or diphosphorus pentoxide. Okay. So in covalent naming, you have prefixes, and every prefix is used unless it's one on the first compound. That's why I like to think of carbon dioxide or carbon monoxide as my kind of like foundation one. So that reminds me, I don't put a one in front of the first element, but I do put a one in front of the second one, which is monoxide. So I like to think of carbon monoxide as my like go-to example in covalent naming to try to prevent mistakes. So never use mono on the first one. Always have a prefix on the second one, regardless, and change it to IDE. Okay. Metals, that's kind of very straightforward, right? You don't really name metals per se. Although the only thing I would say with this is that really be sure of your chemical symbols, right? There are a lot of chemical symbols that aren't necessarily intuitive. I think some people mix up copper and cobalt because they both start with CO, but copper Cu, cobalt Co. Or they'll mix up potassium with phosphorus or sodium with sulfur because they both start with the same letter. But most of these names are based on Latin derivatives, and that's why iron's Fe, because ferrous is iron in Latin. Copper is cuprous in Latin. That's why it's Cu versus Co. Okay. So there, make sure you know the symbols, and they're listed in the periodic table as well. So you should have that, but be aware of that, and so you don't pick the wrong element to get the molar mass for, or write the wrong compound for stuff like that. You don't want to make that kind of mistake. Oh yeah, remember, don't forget polyatomic ions are in ionic naming as well. Okay. Yes. Correct. You do not change the name of polyatomics, and there's 10 of them that you do need to memorize, right? I'm not going to list them all here, but there are like 10 that you need to know. Yes. Yes, you do get a periodic table on paper one. I think they put the names in the back still, but I'd have to double check. Okay. We'll stop there for the table. So that's the end of the table. Okay. Hopefully, y'all. What? Did you keep drawing lines? Okay. Oh, you went over. Okay. Yes. Wait, like up here? Okay. So the next thing, so like I said, we're not going to cover everything in here. If we have time, we'll talk about the giant network covalent stuff, carbon, like graphite, diamond, and things like that. But I want to skip into Lewis structures because if you haven't talked to you before about it, I have a certain way of doing Lewis structures that the way I was taught, and I like it because it works for all structures. It's not it only works for this, it doesn't work for this, and so then you're trying to memorize three different systems to do Lewis structures. This works for everything. Is it sometimes a little slower than the other way? Maybe, but you make sure you get all of them right, and I think that's the appeal to it. And so let me show you how I do Lewis structures here, and it always works. Like there's never a time it doesn't work as long as you kind of follow these steps. Okay. You got it, on? Okay. You're welcome. Okay. So this is the next big thing. We still have shapes and IMFs too. So I guess there's three more things we have to cover. So maybe this one will kind of go to 10:30, 10:45. We'll see. Okay. So here's how I do Lewis structures. Okay. I have two terms here, and I will call this for our purposes the math number. the total number of electrons available to use. So that is the sum of valence electrons minus the charge. Because remember, if you have a negative charge, you're adding electrons. That's why I say minus. Because a negative charge means you have more electrons than you originally started with. And so that's why I say sum of valence electrons minus the charge to get your total. And this number will dictate what your final structure has to be, because these are all the electrons you have to work with. And so that is going to be the main thing behind all this. Okay. So for example, and I know y'all all know what CO2 looks like, but I want to use this as an example to show you how we do this so that you can understand what we're doing here. So for example, if we do CO2, C has 4 valence electrons and oxygen has 6 each. So that means you have 16 electrons, or 8 pairs of electrons to work with in your final structure. So your final structure can only have 8 pairs of electrons in the form of lone pairs and bonds. So those are only 2 ways you can illustrate 8 pairs of electrons. Okay, so always count that up first, because that's going to dictate it. And it feels like a little trial and error, but it's not. There is a method to the madness here, and you'll kind of see it as you do more and more practice. We won't have a lot of time to practice here, but you'll kind of see what I'm saying. Okay. The next thing you do is you draw a test structure. Okay. The test structure is the most basic hypothetical structure possible. Okay. So this is not necessarily the right answer, but it's your starting point. If you start at this point, you will be able to get to the right answer no matter what. Okay. So here's some rules with your test structure. Okay. 1, you give everything single bonds. Okay. So everything gets single bonds. 2, atoms with 4 or more valence electrons get an octet of electrons. Again, this is not necessarily real, but it's your base structure that you will build upon if you need to do something else. Okay. So atoms with 4 or more valence electrons, and you should have calculated that early on because you wrote out how many valence electrons each atom had. So you should know that in this example, carbon and oxygen should both have octets. So what does that test structure look like? It looks like this. Carbon in the middle. And that's your hypothetical structure. Okay, that's your baseline. So in the easiest realm of possibility, everything would have just a single bond and everything would have an octet that needs it. Make sure you star this step, because that's the step that gets people into trouble, because there are some elements that are less than 4 valence electrons that you have to be careful about. Things like boron, beryllium, aluminum. Those only have 3, so you will not give them an octet. They will just be okay with 3 bonds. So watch out for boron, beryllium, and aluminum. Once you draw the test structure, now you compare it to your math number, okay? So how many pairs of electrons does your test structure have right now? How many total pairs does it have? 10. Okay. Yes. 3. Oh, wait. Boron and aluminum have 3, beryllium have 2. So, yeah, so you just got to be careful that sometimes people forget that you have to be, if it has fewer than 4, you don't draw an octet. Because then that'll mess up your whole structure if you don't follow that. But if you do that, you'll be fine. So you have 3 situations here, okay? When you do your test structure, you're going to have 3 scenarios. One scenario is that your test structure, test pairs, equals your math pairs. If that's true, you're done. You don't have to do anything else. Everything worked out, you're fine. Leave it alone. if your test pairs are greater than your math pairs, you need to add double or triple bonds. Because what that tells you is that in the real structure, some of these lone pairs that you drew are actually acting as a shared pair of electrons together. So your test structure is the simplest structure, giving everyone their own pair of electrons. But if you don't have enough electrons to afford everyone their own pair, they have to start sharing more. So that's how you know. So if your test structure is more than your math, you have to start sharing more electrons than you started with. So you have to add more and more bonds to this. Okay? If your test pairs are less than your math pairs, you have expanded octet. That, and you just add pairs to center atom. So if you get 10 test pairs and your math number is 11, that means you have one extra pair. You just put it on the middle atom. That's all you do. There's nothing else to it. You just put an extra pair on the middle atom. Okay. So yeah, if your test number has 10 and your math number has 11, that means you have one extra pair. Just slap it right on the middle of the on the central atom, and that's an expanded octet. Okay. So in CO2, we have 10 pairs versus 8. Sorry, Helena. Hey, how's it going? Um, so that means we have too many pairs, which means we need to change some of the lone pairs into bonds, and that means we need to have 2 bonds. So 10 minus 8 is 2 bonds instead of 4 lone pairs. So where would we add those bonds in this structure? Where would we add those bonds? Yeah, I'm on. Oh, sorry. In this CO2, where would those additional bonds go? Christoph. Okay, between oxygen and carbon. Now, what's the most sensible way to do it? If you've got 2 bonds to add, how would you add them here? One on each side, right? Because you want to be as equal as possible, right? So what you do is this. You essentially say, I don't need these lone pairs anymore. I'm going to put a new bond here. I don't need these lone pairs anymore. I'm going to put a bond here. So essentially what you're doing is you're replacing the theoretical lone pairs with bonds instead. So a bond is equal to 2 lone pairs in our structure here because they're sharing them so that you can both take claim to them. So every time you add a bond, you take away 2 lone pairs that you don't need anymore. And so this structure ends up being this, CO2. And we're going to talk about why this is super important as well later on because, yes, Juan Diego. Not in this specific with C, yes. But again, this is a system that you want to see all the way through for every single molecule. So, yeah, CO2 seems very obvious, but I'm showing you that in the system so you're comfortable with the molecule. But it's a system that applies to every single thing. And you're going to see some issues that come up with other molecules at this. So I'm starting with the easiest molecule here. It's obvious here, but when you get into a bunch of the exceptions and stuff like that, it gets more difficult. So, like, it's obvious now, but we'll see other examples where it's not as obvious. No, but yeah, but you have to start at a baseline. Like that's the simplest possible structure you can make, and essentially you build off on that. Like that's your baseline, and then you can build off of that to get to the right answer all the time. But you have to do that first to know what you need to do. Aman, then Nick, and then Asdi. Sorry, say it again. Yeah, so I cut out 4 lone pairs. Yeah, because when atoms are sharing more electrons, they need fewer lone pairs themselves. Because if you look at this structure here, it now has still 8 electrons to it, right? So we're eliminating these theoretical lone pairs to complete the structure accurately. So when you add a bond, both atoms need one less lone pair themselves. So they're sharing more. No, three lone pairs, not six. Three lone pairs. Yeah. No, a bond is two electrons. No, a bond is yeah, but you count both of those in a bond for each atom. So like that's an octet. Like six lone electrons and one bond is an octet for that atom. No, yeah, I know. That's still eight. You need to stop trying to assign the individual valence electrons for each atom in the structure because that's not what you're trying to do. You're trying to make a hypothetical structure of the actual bonding and then you change it as necessary. Don't try to apply the valence electron rules in this. Don't try to pair up electrons and things like that here. That's not going to work. But this works for everything. Nick, wait, what do you mean? Oh, yes, that's higher level. That's formal charge. Yeah, we'll talk about that in higher level. Asdi, yeah, here. I want you to get out of the habit of just assigning the valence electrons to each atom and trying to make the theoretical the test number make sense. It's not supposed to make sense. It may not make sense in all cases, but it is the fundamental baseline possible structure to make things. And you'll see why this is more important in other structures. Okay. Yeah, I see. Yes. Yeah, math number, math pair, same thing. Yeah. Okay. Okay. Other questions? Yes, Sophia. Oh, because I was trying to explain to Aman that when you add the bond, you get rid of those lone pairs. It still owns eight electrons. So I was trying to show that we cross out those two lone pairs because now, if you look at it, because there's another bond between the oxygen, you don't need that extra lone pair anymore because it can now claim it has eight with those two bonds and those two lone pairs. That's what I was trying to show. Okay. So let me present another scenario here. CO3 2 minus, carbonate ion, for those of you that do not remember your polyatomics. Okay. So we start this way. C is 4. Oxygen is 3 times 6 minus -2 because a -2 means you gain 2 electrons. So that is 24 electrons or 12 pairs. That's our target. That's our target goal. Yes. Yes, correct. Yes. Three oxygen atoms times 6 valence electrons each. Correct. Yeah. So this is all valence electrons only. Do not do total electrons, just do valence electrons. Okay. So your structure should have 12 pairs. Okay. Now, oh, sorry. We're going to save that for a little bit later. We're going to draw our test structure out here. Let me try. So, carbon in the middle. Okay. And that's the theoretical. It's not right necessarily, but it's the theoretical. Now, how many pairs does this one have here? 13. Okay. So that means you have more pairs than you're supposed to have. So what do you have to do? You have to add a bond somewhere. You have to replace some lone pairs with a bond. So Where do you place the bond? One day ago. Okay, which one? Okay, why? Okay, because they're all the same. So when you come into a situation where you need to add a bond and you notice that you have more than one place that you could add it equally, that's your red flag for resonance. So anytime you have a structure where you go, I need to add a bond, but it doesn't matter where I add it, or there's more than one place that I can add it that's the same, that's resonance. So this tells you that you need to add one bond, but you have more than one place that is equivalent. You should think resonance. Yes, Aman. No, no. It's just a when you do the test number and you realize you need to add a bond and you have more than one place to add the bond, that's what you want to look for. It doesn't necessarily have to do with anything with a certain value of a test number or anything like that. Yes, Christoph. Yes. Theoretically. I can't imagine one where that is the case, but yes, theoretically, that would be the case. So what this turns out to be is this. That. That's your structure of carbonate. Yes, Sophia. You have to be really careful about dashed lines. Like I generally, a lot of times the IB will ask you to write all forms of the resonance, and so you want to draw them out. The only thing with dashed lines is I'm afraid because like you have to get the lone pairs right if you do the dashed lines, and I'm still not confident in myself when I do dash lines to make sure I get all the lone pairs right. Because if you add an extra lone pair somewhere where you're supposed to have dash lines and stuff like that, then the whole structure can be off. And so I generally do not have people draw dash lines for this. Because they a lot of times they'll ask you to draw a carbonate, but they'll say show all forms or show all structures, which means you can't draw dash lines. You have to show all three resonant structures. Oh, like sometimes some teachers will teach this as you draw dash lines between all the places where the double bond can be and stuff like that. I've just never really done that. Yes, Sophia. Huh? Oh, that means the overall molecule has a 2 minus charge because that comes from the original molecule. Yeah. Whenever you have an ion, you're drawing Lewis structure, you need to put brackets around it and put the charge on the outside. Yes. Oh, sorry. Sol and then Joe. Joe, I heard Sol first. You don't need to put the brackets. Correct. Joey. Yeah. The bond order for this, let me just make, I just want to check to see if this is, before I say it, I got to really be careful because I think, I'm trying to think if bond order is something that we talk about in here or if it's HL. I just don't want to start throwing much stuff at. They'll say, okay. Yes. The equivalent bonds here would be 1.33. So bond order, we'll kind of mention it here, is essentially the number of bonds divided by the atoms linked. So in this case, it's 4 bonds over 3 oxygens linked. So each bond is the equivalent of 1.33. So it would be closer to a single bond than a double bond in all characteristics, length, enthalpy, things like that. What, Jada? Uh, Sophia. Oh, it's three oxygens bonded to the carbon. So it's like, yeah. So essentially, it's how many of them are bonded to the central atom, I should say. So it's three oxygens. Oh, okay. So let me rephrase that. Atoms linked to central atom. Does that clarify a little more? Okay. And this works for everything. This works for every single Lewis structure you can possibly imagine that you would have to see for IB, especially for higher level where you have expanded octet, because sometimes expanded octet's not super obvious. Like, for example, if you get something like XeF4, which is a possible structure, xenon tetrafluoride, okay? When you do this, xenon has 8, fluorine has 7. That's 36 electrons or 18 pairs. But when you draw it out, okay, you only have 16 pairs. So that means you're missing 2 pairs. So where do you put those 2 pairs? Right on the central atom. So this is a great way to kind of bookkeep your electrons to make sure you drew the right Lewis structure. And as you do it more and more, you'll get faster at it and it'll take less time, but it's kind of the foolproof way to do it. Like, I would much rather you have one way to do all Lewis structures than do it one way if it's a normal octet, one way if it's an expanded octet, one way if it's a sub-octet. It just seems kind of wasteful to have 3 different ways to do it. Yes, Timur? Oh, yeah, sure. So, like, for example, let's say we have something like AlCl3. Okay. Well, Al is 3, Cl is 3 times 7, so that's 24 electrons or 12 pairs. Well, remember, Al has only 3 valence electrons, so you will write the bonds, but you will not give it an octet because it has 3 or it doesn't have 4 valence electrons. So it turns out this is also 12, so you're done. Yes, Jada. Wait, what do you mean? Because Xe has 8 valence electrons. So if you have 4 or more, you have to give it an octet. Wait, what was your question though? Sorry. So like that is expanded octet. So standard level, you don't need to know XeF4, but I'm just trying to show you that it works in all structures and you can double check structures. No, you have to be in period 3 or larger. You can't be in period 2. It has to be period 3 or more. 2 more and then a McKenna. Yes. The ones on the outside should always have an octet. Yes. Yes, McKenna. Correct. So your test structure only had 16. Yeah, the real one has 18. The math number was 18, so you have to add 2 more pairs in the middle. So, sorry. This is your 2 ones that you added to make it 18. Yeah, now it has 18. Sorry. Now 18. Uh, no, it has 8. Well, yeah, technically it owns 12, correct? Because it's sharing 4 pairs and it has its own 2 lone pairs. Yes. It is capable of doing that. Yes. Sure. Ozone follows the very same pattern as carbonate when you look at O3. So O3 is 3 times 6 is 18 electrons or 9 pairs. So when you draw ozone out with the test structure, you give every oxygen an octet, right? So how many pairs of electrons is this, Joey? 10 pairs. So that means you need to add a bond somewhere and replace the lone pairs, right? So which oxygen do you add the bond to? either. And when you say that, that tells you resonance. So ozone can actually behave this way. Oops, sorry. Or this way. So that's what ozone is. It's delocalized electrons because the double bond is moving back and forth across both bonds. And when we measure the bond length here, we notice that they're equivalent. They're not one shorter than the other. They're equivalent, which helps reinforce the idea of resonance. Asdeen. No, because you need to make sure, like, it appears the same, but if we actually number these oxygens, they wouldn't be the same, right? You're thinking that the oxygens, like, if I number this, if I label this as A, B, and C oxygens, this is still A, B, and C oxygens here. So they're different oxygens that are getting double bond. So that it's still the same idea. Yes, Joey. No, they have 6 valence electrons. Only valence electrons, Joey. Wait, where are you talking about? This? This one? Okay. Yeah, but where do those electrons come from? Because the middle one, how are you accounting for all the electrons in the middle one? Because the middle one only has 6, right? Right. So how did that auction start with 8, Joey? Like you're doing two different things and you're assigning electrons like twice so that you can try to account for it. So let me ask you this. Let me go through what you're saying. You're trying to say, let's draw it out. These are the 6 valence electrons of this auction, right? These are the 6 valence electrons of this auction. How many electrons does this in the middle auction need to complete this whole structure? 8. Auction doesn't have 8 electrons. So that's where you have to have a double bond. You were trying to say, oh, these each auctions have 6 electrons, and the bond, there's one on the middle one, but you forgot there's 2 electrons in there, and that second electron in that bond you haven't accounted for anywhere. Because, like, look, if you look this, 1, 2, 3, 4, 5, 6, where are the other 2 electrons? That's why it doesn't work. No, you've already given the other one 6. So that's why you have to do the math number to make sure it checks out, because in this structure, there's too many electrons. You can't afford to draw the structure with the electrons you have. You have a budget here with electrons. Okay. Questions? Okay. Now, to kind of add on to this, we need to talk about once you get Lewis structures, because the reason why Lewis structures are super important is because you have to identify the shape of the molecule once you draw a Lewis structure. And it's not error carried forward. If you draw the Lewis structure wrong, even if you get the right shape of your wrong Lewis structure, it's still both wrong. So super important that you're getting the Lewis structure right before you do that. And so what this leads us to is VSEPR or VESPR, it doesn't matter. It's valence shell electron pair repulsion. Half a page is probably enough if you draw the shapes really small. Okay. So valence shell electron pair repulsion. Essentially what this says is that covalent molecules orient their electron pairs to minimize repulsion. So they create a shape based on the minimization of repulsion between all of those. And so what you need to know is that lone pair has the greatest repulsion, then lone pair bonding pair, and then bonding pair and bonding pair have the weakest repulsion. So if you're going to keep things apart, you want to keep the lone pairs as far apart as possible, and then you keep the lone pairs from the bonds, and then you keep the bonds apart. So that's the hierarchy of the strength of repulsion. And this helps us explain our shapes. And we're only going to do SL shapes now. We'll add HL shapes on after the break. Okay. So if you're HL, you may want to not make these columns as wide because you're going to have two more columns on the right afterwards. So if you want to keep it all on the same table. Yes. Yes, LP is lone pairs. Yes, sorry. Lone pair repulsion is the greatest. As Gene. No. When we do the shapes, when we actually do all the shapes. Okay. Yes. We're going to see that in the shapes. Yeah. So, bless you. Couple more terms we need to know. Yes. If you're higher level, possibly. Charge sensors / electron domains. Okay. When we say charge sensors electron domains, we want to establish that as any lone pairs or atoms bonded to the central atom. It doesn't matter how many bonds there are between it, it's still one domain. So even if there's a triple bond or double bond, it's still one domain. One atom is bonded to it, and that's all that matters. So when you look at a Lewis structure, you're going to count the charge centers or domains in that structure to figure that out. So for example, and this is kind of where our columns are going to kind of occur here. Now, again, if you're higher level, don't spread all the way across the page. You want to keep two more columns to the right if you're going to keep it all in the same table. An example here, 2 charge centers, 3, and then 4 charge centers. Yeah, you'll go do 5 and 6 for higher level. CO2 is our example here. Notice that that carbon has 2 charge centers. It has 2 oxygens bonded to it, no lone pairs. Okay. Now, how would those oxygens orient themselves around the carbon to keep them as far away from each other as possible? Huh? 180 degrees. And so what you see is this 180-degree separation to keep the oxygens apart. What shape does that create in the molecule? Linear. So that's what linear is. Okay. And the angles that I write, you need to know. I think for SL, you need to know all the angles. HL, you don't need to know all the expanded octet angles, but SL, you definitely need to know all the angles. Yeah. No, you don't need to know the expanded octet angles. You still need to know these angles, but for all there's a lot more expanded octet shapes. You don't need to know all those angles. Yes, Sophia. No, two double bonds on carbon. Oh, so if you look at carbon, there's 2 atoms bonded to it, and there's no lone pairs on the carbon. So the number of charge centers you have is 2. Yes. Yeah. So every atom that's bonded to it counts as 1 charge center. And then lone pairs on top of that count as charge centers. 2 for just carbon specifically. Yeah. When we deal with shapes, Sophia, we're only dealing with the central atom. Everything's based around a central atom. Yes. I wouldn't say bonding domains, but just domains in general, yes. Okay. Three. Let's say we have something like BF3. Okay. Notice that boron has three charge centers or three domains attached to it. There's three fluorines, no lone pairs on that boron. Let me zoom in a little bit there. Okay. So if you had a boron in the middle here, how would you orient the three atoms around that central atom so as to be as far away apart as possible? Huh? 120 degrees, right, Trey? Because that will maximize the distance apart from all the bonds. Okay. And when you look at the shape of the atom, it's flat, but it forms with 3 points of what shape? Trigonal planar. You don't get three-dimensional shapes until you get into 4, 5, and 6 charge centers because you want to keep one plane flat to maximize the distance apart from them. So you don't really worry about 3 dimensions until you get to 4, 5, or 6. It's just kind of like stereoisomers in like a higher level organic chemistry. Okay. Now, let's say we have something like um, we'll just do this. Actually, for standard level, it'll be like this. Okay. SO2 kind of has a variety of different shapes, but this is fine for us. Okay. Now, if the S is in the middle, then one of those charge centers that was a bond originally is now a lone pair. Okay. And the other two are still there. Okay. But what does that lone pair do to those bonding pairs? Repels them downward. It pushes them closer together because the lone pair has more repulsion than the bonding pairs. So these end up going toward each other. So the angle gets a slightly smaller. Okay. It turns out it's 117 degrees. It's just 3 degrees less. And that's a good thing to think about. Every lone pair subtracts your angle by 3 degrees. That's a good rule of thumb. Yes, Maddie. Oh, yeah, sure. The lone pair has more repulsion and needs more space. So what it does is it pushes these together because this repulsion is weaker. So it just kind of pushes things, shoves them together. Okay. Now, if I look at this shape, one day ago. Yeah, lone pair is the greatest repulsion. That's this right here. So this is lone pair bonding. So this wins out over this because this is bond pair, bond pair. Oops. Does that make sense? If there's another lone pair, yeah, I'd push it away. Okay. Yes. So, yeah, let me label that here just to clarify. So this repulsion here is lone pair bonding. This repulsion here is bond to bond. And so it supersedes it. Yes, this may. Yes, it's always the angle between the two bonding pairs. Correct. So when we deal with angles here, it's always between the bonding pairs. Yes, Joey. No, not specifically 117. They might ask you, why does the bond angle decrease? And you could say that the lone pair bonding repulsion is greater than the bond pair repulsion. I think, yeah, you could, I think you can say repulsion from the lone pair. That's fine. You can't just say repulsion in general. Now, the shape of it is, the molecular shape of it is what I highlighted here. So what shape do we see here? Bent. So this is bent. Okay. Okay. Oh, yeah, sorry, Sophia. No, it does not. That's a good question. Shape does not change on resonance. Resonance does not affect your charge sensor or anything like that. Oh, I guess ozone would have been a better example here now that I think about it, but same idea. Okay. Let's go to 4. Okay. Let's say we have something like CH4. Okay. This one's a little bit trickier because once you have 4 atoms, you have to take 3 dimensions to spread them out more. So you can't have one flat plane anymore. You have to spread them out. So 90 degrees is not the answer. It actually spreads out into 3-dimensional space, and each angle is 109.5 or 110. If you remember the molecular models we were dealing with in organic chemistry, that angle is what it's making. Like when you angle those carbons and hydrogens from each other, that was that angle, 110 degrees. I would say 110 is fine. Yes, Nick. Oh, no. For Lewis structures, you do not. That's a good question. They will usually specify that in the question if they want you to do it. Okay. Now, for charge sensors is tetrahedral. Tetra meaning 4, hedral meaning faces. And if you think about this, it has 4 faces of hydrogens in the molecule. There's 3 on the top and then 1 on the bottom. 4 faces. That's why it's called tetrahedral. Yes, that's expanded octet. We'll talk about that in higher level. Yeah. So here we see it like this. I'm going to run out of space in this page, and I don't really draw it that great, but you kind of see this kind of 3-dimensional shape here, like that, kind of like a tripod. Now, going further, we have something like NH3, which looks like this. Okay. So now you have the same idea, but now you have a lone pair on top pushing everything down. Okay. What do you think the angle is here then? A little smaller, specifically 107. Just subtract 3 degrees every time. That's a safe bet. 107. The IB does give a little bit of leeway in the angles for some of these angles. These angles that are like kind of adjustable, they're specific. 120 obviously has to be exact, but like 109.5, 110, 107, that's fine. Okay. Now, it's hard to see here, but the shape here is kind of like a tripod. Okay. So what does a tripod shape look like? Pyramid. So it's a pyramid, trigonal pyramid. So this shape here, oops, is trigonal pyramidal. I think you'd be okay with pyramidal, but trigonal pyramidal is the full name. Because there's other pyramidals as well. There's square pyramidal, trigonal bipyramidal, so you may want to write trigonal pyramidal. Yes. Yes. We're going to talk about that in a second. I'm going to do all the shapes and then we'll talk about which ones are which. That's a good question. Okay. Now, water. H2O is going to look like this, where you have two lone pairs apart from each other. Okay. Let me zoom in a little bit. I can't zoom in. Oh, yeah, I can. So, what's this angle going to be here? If you had to guess, 104 is fine. 104.5. Maybe in college they're more nitpicky about it. It's 109.5 and 104.5. But for the IB, they'll say anything. Take anything between 102 and 106. They'll take. So 104 degrees is a good value here. Now, what's the shape of the atoms in this molecule? Bent. So there's two bents you have to know. There's a bent with one lone pair and two bonds, and there's one with two lone pairs and two bonds, and the angles are different. Notice this one's 117 and this one's 104. Make sure you differentiate between those angles. Questions? Okay. Those are all the shapes you need to know for SL. So 6 shapes in total. Okay. Now, what we just did, all 6 shapes are considered molecular geometry because it is based on the atoms arrangement. Because you notice when I highlighted here, I only highlighted the bonds. I ignored the lone pairs. So the 6 shapes we did here are all molecular geometry. Okay? So all 6 shapes we did here are what we call molecular geometry. The difference is in electron domain or electronic geometry, you look at lone pairs and bonds the same. So you highlight all of them. You highlight all the lone pairs and the bonds on the structure. 9. Yeah, there's 4 under 5 and 5 under 6. Yeah. Okay. Huh? You might be able to just close. Okay. So electron domain geometry does not differentiate between atoms and lone pairs. So if you highlight electron domain geometry, let me ask you this. If I highlight the electron domain geometry, meaning I highlight all the pairs around the middle atom, are these two different? No, they're the same. Because we don't care whether the lone pairs are bonds, they're the same number. So electronic geometry is much more limited. There's only 3 electronic geometries you can have. You can only have linear, trigonal planar, and what? Tetrahedral. So these are the only 3 electron domain geometries you can have. Because in electron domain, you don't care whether it's a bond or lone pair, it's all the same. So if you have 4 charge centers, it's always tetrahedral. If you have 3 charge centers, it's always trigonal planar. It's when they ask about molecular geometry where you're looking only at the atoms where the shape changes when you add lone pairs. Sophia, question? Yes. They're both classified underneath. They're both classified as electron domain geometry of trigonal planar. Does that make sense? Timor and then Amon. Correct. So you're not going to look at bond lengths for geometry at all, really. The bond angles. Oh no. Like yeah, you wouldn't look at bond angles. So yeah, be careful because they might ask you state the electron domain geometry and molecular geometry of this shape, and they might be the same, they might be different. So be careful because I don't know which more. I don't know what's trickier if they're both the same answer or if they're different answers, right? Because some students think they can't be the same, so they change it. Then other ones think, well, what's the difference? And then they get that wrong anyway. So I don't know which one's quote unquote trickier to ask. Yeah. Okay. Oh, sorry, Amon. What's your question? Yeah. There's no more three and four. Like it's all five and six. There's four fives and there's five sixes. So it's just gonna keep going down further there. Yes, Sol. Yes, correct. Let me you know what, let me add that to the notes here. Okay. So if I were doing this, I would say two are all linear, three are all trigonal planar, and four are all tetrahedral for electron domain geometry. So we can add that in there. Okay. We're gonna run a little bit over. We're gonna do IMS very quickly, and then we'll take a break and we'll do HL. This, yeah, yes, those are the only things. Now, just to clarify, Juan Diego, your electronic domain can be the same as your molecular. If you don't have any lone pairs, they're the same. It's only when you start getting lone pairs on center that the geometry name changes. Okay. So, like, if you have all three bonds, the electronic geometry is the same as the molecular geometry. It's when you start getting lone pairs where the name changes. And for SL, it's maybe less important, but for HL as well, what I do is this. Okay, I draw out these three to help figure things out. So this is what I do. I draw this, and this. Because if I draw these electron domain geometries, I can figure out all my other shapes by just covering up lines on the structure. So I draw these shapes out, and then I just start covering things up. And so, for example, what I'll do is like I'll say, okay, trigonal planar. Well, I have one lone pair, so I'm going to cover up the top line here. And what's left? It's bent, right? Here, tetrahedral, I cover one up, three pointing down, pyramidal. And then I cover two of them. What's left? It's bent. So, oh, because it's three pointing down like this. Think of my fingers right here. So it's like three dimensions. I'm not really showing it here. But so for SL, if you just know the three electronic geometries, you can deduce the rest of the geometries just by covering up lines. Now, it's less important because it's 6 versus 3. For a higher level, it's 15 versus 5. So it's kind of a big difference between that. So it'll be more important in higher level where you have more and more bonds to cover up. But it is still a useful trick to minimize what you have to memorize. If you know your three electronic geometries, just cover up a line every time you have a lone pair, and you'll be able to figure out the rest of the shapes. It'll prevent you from mixing up bent and linear, right? Because sometimes people say, oh, there's two bonds that must be linear. I'm like, no, the lone pairs make it not linear if you look at these shapes here. Yeah. So, oh, what I was saying is that if you don't have any lone pairs on the central atom, Juan Diego, the geometries are the same name. That's all I was saying. Yeah. Yes. Yeah. If you have two lone pairs on a four charge centers, then yes. But if they're four bonds and four charge centers, then they're both tetrahedral. Yeah. We'll get in there in the higher level. I don't want to stress out the SL kids. Yeah. What's up? Oh, yes, but then it's just linear because when you only have 2 points, it's always just linear. Oh, so Sarah asked a good question. Could you have like three charge centers with two lone pairs, but anytime you only have two atoms, regardless of how many lone pairs you have, it's just linear. Okay, last thing for today, and then we will stop. Yes. Um, not how many lines you got? I mean, you can go left and right. That's fine. Okay. IMF, the covalent molecules. I'm not going to go into bond polarity and stuff like that. I want to just focus on molecular polarity because we're kind of running out of time today. But so molecular polarity is what determines IMFs. And so that's the overall polarity of the molecule. And so I'm going to draw three structures here. Let's say this, and then this. Okay. Now, molecular polarity is how does a molecule overall as a whole polar or not polar? When you look at CH4, is there anything on the outside of the molecule that's different than the rest of the molecule that would create a disparity in polarity? No, it's uniform all around. So this is considered nonpolar because everything's equal on the outside. It's always the outside of the molecule that we really care about. Okay. So if it's nonpolar, its strongest attractive force are London dispersion forces. London named after a scientist, not the city, by the way. There is a scientist with the last name London. That's why it's called London dispersion forces. Now, all molecules have LDFs. So like every molecule has LDFs in some form or another. It's just not always a priority. And these LDFs come from temporary dipole moments. And I'll explain to you what that means in a second. Yes. Oh, it's a nonpolar molecule, which means it exhibits London dispersion forces as its strongest attractive force. Okay. A temporary dipole moment. This is why London dispersion forces are super weak. London dispersion forces are not constant all the time. Okay. What happens is that in every molecule, electrons are constantly moving around between atoms, right? And every once in a while, the electrons will be imbalanced on the molecule, which will create a temporary pole. And so it's like if I had y'all kind of bouncing around this room as electrons in a molecule, at any given point, there might be more kids on one side of the room than the other side of the room, right? So there would be an imbalance. And what would happen is that imbalance causes a chain reaction amongst all the other rooms to imbalance as well. And that's what a temporary dipole moment happens. So in any molecule, when the electrons are constantly moving around, temporarily there'll be a little bit of positive and a little bit of negative, which causes the molecules around it to react to that, which causes a very, very weak attraction. So it's very, very weak. Okay. But it increases with mass. Okay. So the larger the mass, the stronger the LDFs that are occurring. So if you're comparing two species that are nonpolar, the one with the greater mass is always the stronger one. And you can see this best explored by the halogens. Because if you think about the state of matter of F2, it's a gas. Cl2 is also a gas. But what's Br? A liquid. And then I is a solid. So you can see the state of matter increasing in strength as you go down, as it gets more and more massive. So gas, gas, liquid, solid. So you can see that LDF reinforcement of that concept in the halogens states of matter. With HCl, you have a polar molecule, which means it exhibits dipole-dipole, which means a permanent dipole moment, meaning that there's always a positive and always a negative. So there's a constant attraction and repulsion between all the molecules. So that's why it's stronger. In terms of a molecule with similar masses, by the way. Again, we talked about that in organic chemistry. You can only compare the strength of these when you have similar masses. Sometimes the mass gets so different that you can't compare the strength of these. But so with HCl, you can notate it like this or like this to show the polarity in the molecule. You can arrow point toward the negative, or you can write partial positive and partial negative as a way to notate that polarity, that permanent dipole. Yes. What do you mean draw out IMS? Oh yes, they could ask you to illustrate the attractions between several molecules of the same type. Yes. Usually you'll see that with like dipole dipole or hydrogen bonding. And so I'll show that with hydrogen bonding. Oh, that arrow shows you, it points direct toward the negative region of the molecule. So you think of it as a plus sign being the side, side of the arrow with the plus sign is the positive end. It points in the direction of the negative part of the molecule. Electronegativity. Yeah. In this case, easy because Cl is more electronegative than H, so it's going to point toward the Cl. That means that there is polarity. That means there is a positive end and a negative end of the molecule. Yeah. Bless you. Now, oh yes, Azine, sorry. Oh, gas, liquid, solid. So that's a state of matter at room temperature, just to reinforce the idea as it gets more massive that the IMS gets stronger. Okay. Hydrogen bonding is a unique, stronger dipole-dipole. It's still a dipole-dipole, but it's a very increased one. Which we call hydrogen bonding. And it only occurs in specific scenarios where H is bonded with N, O, or F. It's not enough to have it on the same molecule, H and F, or H and N, and H and O. It has to be directly bonded to that to create enough difference in polarity that it becomes strong enough. So, for example, ammonia, NH3, has that, N bonded to H. And so what you'll see is that when two of these molecules come into contact with each other, there is hydrogen bonding between the very negative part of the nitrogen and the very positive part of the hydrogen on another molecule. So that attraction between the H and the N, that's your hydrogen bonding. Yes. Yes. Jada. Yes. It's definitely polar for sure because hydrogen bonding is a stronger polar attraction. So it's like a super polar. Yes. Oh, there. Now, be careful when you're labeling this because the attraction between the molecules is hydrogen bonding. What is this that I'm pointing at right here? A covalent bond. Okay, there's a difference. So they might have you label it. Yes, Shada? Okay, covalent bond versus a hydrogen bonding that's across attractions, across molecules, an intermolecular force of attraction. So notice here, really emphasize that hydrogen bonding occurs across molecules, a covalent bonds within a molecule. Wait, say it again. No, it's not as strong as a covalent bond. It's very strong, but it's not as strong as a covalent bond. Correct. Yeah, that's why I don't like the name of that amon. They're not exactly an actual bond, but they're almost the strongest one. Jada and then Nick. That's what makes it very, very negative. Like it's not actually physically bonding with it. It's just really strongly attracted to it. So the H is very positive. It's very strongly attracted to the negative electrons at the end. That's what it's attracted to. Yes, correct. Yeah. So, yeah, I know what you're saying. So within a molecule, they're covalently bonded to each other. But this nitrogen is hydrogen bonded to the hydrogen on another molecule. So they're not actually physically combined connected. So you have to make sure you distinguish that. Nick and then Sarah. Not really. There's nothing that you would talk about to make it stronger. I guess you could talk about like which ion, which atom N, O, or F is with it, but no, you wouldn't have to differentiate between those two in an IB exam or anything like that. Yeah. This helps you identify which molecule, if they all have the same mass, has the strongest IMAPs, which then leads us to the physical properties like boiling point, like like volatility, things like that. So, which of these three molecules has the highest boiling point, Juan Diego? Not LDF, right? It would be hydrogen bonding, exactly. So, if you had these molecules say, oh, this one has hydrogen bonding and they're all about the same mass, that one should have the highest boiling point and the lowest volatility because volatility is how quickly it evaporates. Wait, what do you mean? They're attracted to each other. It's not an actual, like, that's why I don't like the term hydrogen bonding because it's not an actual bond. It's a force of attraction that's just very strong. And so, like, they're not actually going to bond with each other. It's just such a really, really strong attractive force that's stronger than any normal dipole dipole to kind of keep the molecules closer together to affect their physical properties. Yeah. Sarah and then Jada. Oh, so the negative is on the N and then the positive is on the H side. I see what you're saying. So let me move this down a little bit. Like, is that better? Jada, question? You're good? Uh, Timor, you not comparing them. No, hydrogen bonding is stronger than dipole. Dipole is stronger than LDS, but covalent bonds are far stronger than any of those. I just wanted to make sure you could know which one's which if they ask you to identify them. Because I've seen before they'll say draw the interaction between two ammonia atoms, two ammonia molecules, and label where hydrogen bonding occurs and label where a covalent bond is occurring. I've seen that question before. Hmm. Yes, correct. Yes, CH4 to CH4. Okay, questions. Okay. Oh, yes, I'm on. Yeah. So that's essentially topic four in a giant nutshell for SL. I know normally it would take me about 3 weeks to cover all this in class, but this is kind of a cliff notes because hopefully you've seen a lot of this before. So this is the end of the SL section. We are going to take a 10-minute break, come back and do an hour of HL. So I'm going to pause the recording right now. Okay. So we're recording now. Okay. So HL shapes. This is where expanded octet, this is where Lewis structures really come into play, where you have lone pairs or extra bonds on center. And so when you have five charge centers, you will need to orient in 3D space, but a little bit more difficultly. So you want to have one 180 and then a trigonal planar kind of bisecting it. So let me do it this way. because now that we've done wedge dash, you might be able to kind of visualize it a little bit better that way. It looks a little bit like this. Okay. So something like PCl5 that has 5 charge centers is going to look like this. And it has a very specific shape name, okay? What you want, I drew it sideways, but what you want to think about is this. You want to think of it as like an atom here, and then the 3 parts where my fingers come together is the other 3 atoms. And so it's actually what we call a trigonal bipyramidal, because it's 2 pyramids stacked on top of each other, base to base. And so this shape is trigonal bipyramidal. Okay. So that is also the electron domain geometry. So if you have 5 charge centers, no matter how many lone pairs you have, it's trigonal bipyramidal. Jada? Okay. Now, let's see. Hold on a second. I think SCl4 works. Sorry, I don't memorize all these examples off the top of my head, but I think this works. Right? 6, 28, 34. Yeah, that's right. Okay. SCl4. Now, here's the thing. These 5 charge centers are established right now. Which of these lines, on average, is the furthest away from each other? The one on top. Okay. So what we're going to do is we're going to replace that one on top with a lone pair. I'm going to change color just so it kind of stands out a little more. Okay. So the one on top is the first one we replace. Now, what's the remaining shape of the atoms when you take away that line? Seesaw or sawhorse, depending on what textbook you look at. So what you're left with here is a seesaw shape. Yes. Sawhorse is another name for it, yes. Like, depending on, I think British textbooks will say sawhorse because a sawhorse is used in woodworking. It's like that long kind of wooden with 2 kind of legs to where you can cut wood and stuff like that. Yes. Yes, that's a good point. So, oh, sorry, I got ahead of myself. I didn't talk about the angles for the first one, but you don't need to memorize these angles here. But you're right, Christoph, that the other angles would go down a little bit. And so, like, it would press downward here and make these angles a little bit smaller. No, but up here, you do need to know that it's 90, 180, and 120. Actually, don't need to know the 90. You just need to know the 180 and 120. So the Y forms a 120, and the line itself is 180. So you do need to know those 2 angles for the original shape. Correct. Like, you don't need to know specific angles for the ones down here. You just need to understand, like Christoph said, that if they were to ask you the angle, they would say greater than or less than a certain thing. And so then you'd have to be able to understand the lone pair makes the angle smaller. But they wouldn't want a specific number. Okay. Let's go to, oh my goodness. It's sometimes it's hard figuring some of this stuff out. Does that work? Yeah, I think that works. Okay. Kind of making these up on the fly. Some of them may not be real, but you get the idea. So let me ask you this. If we look at this shape up here, okay. Oh, sorry. I meant to cut it. And I wanted to pick the place where the next lone pair would be as far away from the other lone pair as possible. Because remember, you want to keep the lone pairs as far away from each other. Where's the next line that I would take away? Which line would I want to take away that's furthest from? Yes, Juan Diego. Yeah, because those are 120 degrees away from them. They're the furthest away, right? Well, you would never have to draw it, but yes, you could just do that. So let's just do this. Let's take this off here. I'm just going to draw it as a lone pair like we did before, like that. Okay. So what shape is left that I've highlighted now? Hint, it's a letter of the alphabet. Yes, Landiga. T-shaped. So, okay. No, we were looking for Q. I'm kidding. Okay. T-shaped. With a hydrogen, carbon, a methyl group coming off. Yeah. Okay. No, no. Okay. So notice again, we're starting with the initial shape and we're just taking away lines from that shape to figure out all the rest of the structures. Minimize what you have to memorize. If you know the original shape, you can just start covering lines up and you'll come up with all the other shapes. Jada. Okay, cool. Glad I could help. Yes. Oh, okay. I see. I think I see what you're saying. So you're asking me to redraw this. Does that look better? So Sarah asked me to redraw the structure with wedge and dash with the actual lone pairs and stuff like that. So I drew it like that. Yes. Yeah. Yeah. They should be kind of on the same half of the molecule too. I had some kids drawing wedge dash like opposite directions and stuff like that, and that's not usually the way you do it. Okay, next one. I3 minus. Okay. You take this same structure, and let me ask you this. Okay. Which line is now the furthest away from the other two lone pairs? Soraya. Yes. Okay, Aman, which one's the furthest one away? Which line is the furthest away from the two lone pairs we have already here? Hold on. Aman. Which one do you think, Aman? The wedge. Because the wedge is 120 degrees away, everything else is 90 degrees away. Correct. So that becomes this. Okay. So what's left in this shape? Linear. Okay. This is linear. Why is it linear? We've got lone pairs here. How does something become linear if you've got a bunch of lone pairs repelling each other? What must be true about the lone pairs in the structure, Nick? They have equal repulsion in equal and opposite directions. So the magnitudes are all the same, so they cancel out. Yep, exactly. 120 degrees. So the vectors cancel each other out exactly. So, like, if you're thinking about the vectors here, you have this repulsion this way, and this way, where you have a net repulsion of zero. So this is one of the rare cases where linear can have lone pairs. Okay, that is the last five one. Yes, Sol. Yeah, trigonal bipyramidal. It's always the first molecular shape you can have. Okay. To repeat what Sol said, the electronic geometry for five charge sensors is trigonal bipyramidal. So it's the first shape that you have in every row is the electronic geometry. Okay. Again, if I'm doing this myself and I'm trying to minimize what I have to memorize, this is the shape I would draw. I would draw this shape right here. Oops, sorry. Okay. And what I would do is every time I have a lone pair, I would take away a line. And the first line I would take away is the top one. So if I know this shape is trigonal bipyramidal, the first one I take away is this. That becomes seesaw. And I take away this one. That becomes T-shaped. And then I take away this one, linear. This is how you minimize what you memorize. If you know the original shape, you can just start taking away lines and figure out the rest of the shapes without having to memorize five different shapes. Because it's very intimidating to think of memorizing 15 shapes, whereas you could just memorize 5 shapes. Doesn't that sound a lot more appealing? Okay. Questions about this? Okay. Good work. Okay, 6 charge centers. This is the longest column, by the way. Yes. Okay. 6 charge centers. So let me ask you this. Okay. SF6. If I have 6 points to distribute around in 3-dimensional space, how would I distribute them around 3-dimensional, Christoph? Kind of like a cube, and in math, it would be kind of representing what? The X, Y, and Z. Right. So it turns out it looks like this, like the X, Y, and Z axes in math. But we call it something different because when you think about X, Y, and Z, and you think about the quadrants in X, Y, and Z, how many quadrants are there actually when you have X, Y, and Z? 8. So this is why it's called octahedral. That's why it's called octahedral. Even though it has 6 points, it forms 8 faces. So this is octahedral. So tetrahedral means 4 faces. Octahedral means 8 faces. Now, what are all the angles if they're X, Y, and Z? 90 degrees. Okay, so that's a good start. Okay. Okay. SF5 minus. That means S with a lone pair and then 5 Fs next to it. Okay. Does it matter which of these points I make a lone pair? No. So for sake of visual, I will take off the top one because I've taken the top one off of every single one before that. Okay. So what shape is left with this structure? Okay, how'd you get that, Arda? Okay, so how do you see a square pyramid here? Let me rephrase that, Arda. And then coming to that point right here, right? So I just want to make sure that everyone sees what that is. It's a square pyramidal because the top 4 make a square, and it comes to a point. That's where the square pyramidal comes from. So this is square pyramidal. Yes, top is lone pair. Yeah, let me draw that in there. Like that. Good. Yeah, SF5 minus. Okay, let's keep going. I think y'all are starting to kind of get the hang of how do we deduce each of these shapes. So we do XEF4, where it has 2 lone pairs on the XE with 4 bonds on the F. Okay, so what line am I taking away from next if the top line is the first one I took away from? Jada? Which line is furthest away from the lone pair? Exactly. So you take that one away. Okay. So what shape is left when you have a lone pair on the top and a lone pair on the bottom and you've got 4, Joey? Square planar. Because the lone pairs cancel each other out, it flattens it out. So this is square planar. Okay. Oh, I don't know if I have another shape here. I don't think I should know it. I think TEO3. Anyways, let me just keep going with shapes here to speed things up a little bit. We don't need to know examples for everything. But if I were to add another lone pair, replace another line with lone pair, does it matter which one I replace? No. I'm going to do this one just so it's easier to see. Sorry, let me redraw this. So this one stays. I'm going to draw in a lone pair here. It's kind of hard to see, but what's the shape now? T-shaped. It is T-shaped again. You'll see it again. Okay. Okay. So, like you said, Juan Diego, where's the next line you're taking away from? Here. Yes, the one that's perpendicular to the rest. So then this becomes linear. And that's all your shapes. You know, perpendicular to the line that was drawn already. Yeah, not perpendicular to the lone pairs, but so linear. So if you know the original shape, if you just keep covering up lines that are farthest away from each other, you could deduce the rest of the shapes. Yes, when you cover up lines, that represents a lone pair. Exactly. So minimize what you have to memorize. See if you can do this to help. Because look, IB chemistry is a lot of memorization already. You know that from organic chemistry. I don't think you want to waste memory memorizing 15 shapes when the chances of having like one shape on the test is most likely. Why waste 15 pieces of information in your brain when you have so much other stuff you could be doing? Keep it down to 5 and then just figure these out when you need them. Okay. Now, if you can memorize them and you still have plenty of space in your memory, go for it. But I just think there's so much stuff here that if you can kind of figure this out on the fly, it will reduce how much you need to actually memorize. So memorize the electronic geometries and then figure out if you can teach yourself how to break those down into different shapes. Okay. Only the first ones I wrote. Yeah. Oh, I guess 90 and 120. I think they want 90 and 120, to be honest with you. Now that I'm thinking about it, I don't think they have 180. They want 90 and 120. Those are the two angles they want. And then 6 charge centers is 90. That's all you need to know. Oh, sorry. Here. Oh, yes, Jada. Yeah, what's the bond angle in the structure between the two like between the atoms? Yeah. So they'll say, what is the bond? What is the FSF bond angle? You're welcome. FSF bond angle in SF6. So you say, oh, it's 90 degrees. Oh yeah, sure. 90 and 120 for trigonal bipyramidal, and then just 90. Everything's 90, correct. I guess you could argue there's a 182, but like 90 is the only one you really need to know. Yeah, no, okay. Sorry, 90 and 120. I changed my mind. I think it's they'll ask you 90 and 120. Wait, what? No, I'm having trouble coming up with an example off the top of my head, so I'm gonna say no. Okay, yeah. Yes. So yes, Jada's right. To be able to do this, you have to draw the Lewis structure right before you get this. And so that's why I spent a lot of time on drawing Lewis structures because you have to get that right to get this right. Because there's no error carried forward. It's not like math, like calculations where if you make a mistake, you carry it through. No, if you draw a Lewis structure wrong, and even if you name the structure of that Lewis structure right, it's still wrong. So it kind of stinks. Yes. Yes. Well, I mean, you mean the shape? Trigonal bipyramidal and octahedral. Yes. So it's always the first shape in the column. That's the electronic geometry. Okay. All right. So that is all the shapes. Okay. It was a relaxed mentor. He just messaged. He goes, "Yeah, it's my bad." He goes, "It took me 5 seconds to realize you were teaching chemistry, and then I just walked out. I didn't even see him walk in. Honestly, I was like so in the zone, like I didn't realize he walked in and out." Yeah, he's probably having flashbacks because he's an engineer, so he took this chemistry class like in college. So he's like, "Oh, yeah." What do you? Oh yeah, sure. That's so, that's so funny. I'm gonna give a hard time about that. Okay, what? Oh, that would be the ones I circled right here. Trigonal bipyramidal and octahedral. Those are the headers. Those are the electron geometries. Okay. All right. So next thing is hybridization, and then we'll finish our formal charge. It's the one that will take the shortest amount of time. So I would good luck. I'm not agreeing to anything here. Okay. Hybridization might be kind of tricky. Okay. Yes. Yeah, I think that's enough. For hybridization, at least. Formal charge, you can do on the next page. Okay. So we talked about this in higher level this week, but I want you to understand what hybridization is. Okay. I'm gonna cite this exactly the way um, they have it. Hybridization is a mixing of atomic orbitals um, to form bonding orbitals. So the idea is this. If you remember atomic orbitals from last year, an s orbital looks like this, and p orbitals look like this, x, y, and z directions. Okay. The problem is because these shapes are different, when things try to bond together, things would be bonding in different lengths and different places that don't make much sense energy wise. And so what happens is when an atom wants to bond with things, it takes these orbitals and changes them into equal hybrid orbitals. And so you kind of saw this in the HL section where they'll morph into what we call hybrid orbitals. And these are called sp3 orbitals because it takes one s and three p's to make four orbitals. And that's always true. The number of atomic orbitals you need is the same number as hybrid orbitals that you're making. Yes, Joey. Average lower energy, yes, possibly. But I don't think you're going to have to define hybridization. You just need to be able to identify it. Okay? Because none of these are lower than S. They're in between the energy of S and P as a whole, right? So like if P is high energy, S is low energy, then sp3 orbitals are right somewhere in between. Okay? So these are what hybrid orbitals are, and they orient themselves in the Vesper shapes that we just talked about in a certain structure. These hybrid orbitals are used for sigma bonding and lone pairs. And we will talk about what sigma bonding is now. Okay. A sigma bond, or written like this in the Greek letter, sigma, that's a sigma bond. Okay. Is the direct head-on overlap of two orbitals between nuclei. So a sigma bond is the first bond between two atoms, and it happens between the two nuclei of the atoms in question. So this bond, it's taking up the space in between the two nuclei. It's the strongest of the bonds that are possible, and it's also the first one that's possible. It's the easiest one to make. Yes. Well, see, the IV definition says atomic orbitals, but like it's not though. Like it's really hybrid orbitals. The only atom that would be atomic orbitals is hydrogen because they don't have any hybrid orbitals. So it says it in the definition here, It says overlap of atomic orbitals, but it's not really atomic orbitals here. It's hybrid orbitals. So I don't know. So what you want to imagine is that, like, if you had a carbon and another carbon, the first bond between them is that sigma bond that's happening between them, and that's a hybrid orbital between the two. Lone pairs also are in hybrid orbitals because they have to prepare for bonding if necessary. No. It is a combination of s and p orbitals. Yes, it's two hybrid orbitals that are happening. Right. So this occurs due to hybrid orbitals. Oh, that they prepare for bonding by being in hybrid orbitals as well. So all of your hybrid orbitals are used for sigma bonding and any lone pairs on that atom that in question. So if you want to try to figure out how many hybrid orbitals you need, you add up how many original single sigma bonds there are and then how many lone pairs. So for example, let's say we have something like CCl4. The hybridization around C, okay? How many sigma bonds does that carbon have? Juan Diego, don't distract you. Okay. How many sigma bonds around the carbon? 4. So there's 4 sigma bonds. Because it's the first bond between two atoms is always sigma bond. 0 lone pairs. So that means you need 4 hybrid orbitals. So carbon is going to take from its orbital inventory to make those hybrid orbitals. And to make 4, you need 1s and 3p. So the hybridization is sp3. That's how you determine that. You look at the Lewis structure and go, how many lone pairs and how many sigma bonds are there? That's how many orbitals I need. So I'll take from the s, 1s, and then from all the p's that are necessary. Yes, Joey? No, we're going to get to that in a little bit. Yeah. Okay. Yes. From the outermost energy shell of carbon. So the outermost shell of carbon has an S sublevel and a P sublevel that can be used for bonding. Yeah, well, even they have those orbitals whether they have the electrons or not. They're all available to hybridize. So because if you think about carbon, that's tricky because when you think about carbon's 4 electrons, 2 of them are in the S and 2 of them are in the P because they're different energies. But when it hybridizes, now that they're all the same energy level, the electrons can distribute equally across, and that allows the bonding to occur. Okay, so that's another thing. I guess what Timur is saying is something I want to harp upon is that this helps explain why carbon, which is 1s2, 2s2, 2p2, if you think about it, this doesn't make much sense to allow for carbon to bond 4 times because it already has 1 lone pair and 2 single electrons to share. But what happens is carbon hybridizes them into sp3, so now the 4 electrons can equally distribute and bond 4 times. Juan Diego, and then Jada, and then Sarah. Oh, those are the orbitals. Those are the atomic orbitals that you're using to make the hybrid orbitals. Every atom has those available in their outermost shell. Like, that's what I was showing down here, carbon, right? Carbon's electron configuration is 1s2, 2s2, 2p2. So carbon has a 2s orbital and 3 2p orbitals to hybridize with. Every atom has those s and p orbitals on their outermost shell. Why are you looking at me that way? So, no. S means the s orbital. So look, do you see these orbitals right here, Juan Diego? What we're doing here is we're taking the s orbital and the 3p orbitals, mashing them together and forming 4 brand new orbitals that are the same. So that's what this SPP stands for, is this S and these three p orbitals that are changing to allow for new bonding? Three separate boxes. Okay. Oh, Juan Diego, what's your question? Hold on, broke. Okay. A sigma bond is always a hybrid orbital. Yes. So, like the way you want to do this is Juan Diego is you want to look at a Lewis structure because you should draw the Lewis structure first. Okay. When you have the Lewis structure, look at how many sigma bonds and how many lone pairs you have around the atom, and that will tell you how many orbitals you need to hybridize. So, for example, in this, you see how carbon has four sigma bonds and zero lone pairs? That means you need four hybrid orbitals. So how is carbon going to make four hybrid orbitals? It's going to take its s orbital and its 3p orbitals and make four brand new orbitals of those four orbitals. Lone pair still counts as a hybrid orbital. So if it's 3 and 1, it's still the same. We're going to talk about that in a second. We haven't done that yet. Yes, Shada. So, okay, normal carbon has 2s2 and 2p2, correct? Which doesn't make sense if carbon's trying to bond four times. So what happens is those orbitals of different energies come together and make four equal orbitals. And when they're equal, then the electrons can distribute across them. So let me redraw that. Okay, let me show you what I'm talking about. So when we draw the energy levels here, it's this 2s, 2s and 2p. That's why S fills first. But what carbon does to allow for four bonding is it does this. It takes all four orbitals, averages them out so that they're all the same. So now when the electrons fill, they fill like this. And that allows it to bond four times. Yeah. Yes. Yes. And they all come together and form four identical ones. It's kind of like the analogy I gave yesterday with the like dollars. Like the S is like a $5 bill, and then the P's are $1 bills, and you're trying to get four $2 bills so that they're all equal. That's what's happening here. So you can bond four times. Yes. Lewis structure. You don't even need to worry about configuration. Honestly, like the configuration is just to help you understand what it's doing, but you don't need to write that out the configuration. That's probably a waste of time. Okay, what you want to do is draw a Lewis structure and then count how many sigma bonds and lone pairs are on the central atom. Because that'll tell you how many orbitals. It doesn't matter how many valence electrons you have, because every atom has those orbitals available. Whether they're filled or not, it doesn't matter. That they're always available. So don't worry about the Lewis structure. The electron configuration. That's just to help you understand what was going on. Okay. Oh yeah. Let's see. Hold on a second. Arda, and then back this way. It would be some kind of hybridization. Yeah. This way and then Juan Diego. Yes, by sharing electrons, correct. Juan Diego. Electrons, not atoms. Then some of those are going to end up being lone pairs and not sigma bonds. So that's where you get some of the lone pairs on some of the atoms. Oh, because it's only the outermost shell that bonds. Yeah, you only count the outermost shell. Joey. Yeah, it makes the ideal structure, correct. Okay. Now, what we didn't talk about is this next part, which is pi bonding. Well, we talked about it in benzene a little bit, but pi bonding occurs in the parallel or sideways overlap of unhybridized p orbitals. Okay. So because the sigma bond happens between the two atoms, there's no other place to have extra bonds in between the atoms. So the next way atoms bond is they form other regions where electrons could be shared. And so what happens is an atom, sorry, like let's say pretend this carbon's bonded to this oxygen and you want a double bond. The p orbital exists in this state so that the electrons can or kind of overlap between the space, and this is what we call a pi bond. So we have a sigma bond in here, and then we have a pi bond on top of that sigma bond. That's the second part of the double bond. Okay. Yes, Joey. Yeah. Well, I'm telling you, the electron configuration doesn't tell you that. The Lewis structure will tell you whether you need it or not. So let me show you what I mean by that. Okay. So understand first that the pi bond is the second bond. It's weaker than a sigma bond, but it does add some strength to it. So like a pi bond isn't the same as a sigma bond. It's weaker, but it still adds strength. So let's say, for example, remember CO3, 2 minus? Okay. This carbon, the one I'm pointing to here, how many sigma bonds does it have linked to it? 3. One for each carbon. So 3 sigma bonds, 0 lone pairs. So how many hybrid orbitals do you need? 3. 3 hybrid orbitals. Okay. Yes. So it would be sp2. So you would use sp2 hybridization to do this. Okay. Where's the extra p orbital going then? Into the double bond. So that double bond that we have with the C double bond O at the top, that's where the extra p orbital that's unhybridized is going to help support. Do you understand that one, Diego? Um, no, what you want to think about it is that if we're doing this with this, what's happening is this. Because one of the p orbitals is staying by itself to allow for double bonding, and the other 3 hybrid orbitals. So this is sp2 right here. And the 4th electron is what's causing the double bond between the oxygen and it. P. So these are p orbitals and these are s orbitals, right? When they hybridize, they become medium energy. But for C in here, you need 3 of those middle energies, and you need 1 p orbital alone to create the pi bond that's between the carbon and the oxygen. So one of them is unhybridized. So this one is unhybridized. You leave it alone to allow for the extra bonding. Oh, like this? Oh, no, Juanico, you only hybridize these 3. Like, no, Juanico, you don't hybridize all 4. You only hybridize 3 of them, the ones I circled. If you hybridize 3 orbitals, you make 3 hybrid orbitals. So this orbital here, Juanico, is this orbital right here. Okay? Well, the electrons get reorganized when the hybrid orbitals happen. Like, you're not going to fill this up exactly the way you filled it up here. So stop trying to move these electrons around. Take all 4 of them out and then fill them up again from scratch here. Stop trying to move them around in here. These are brand new orbitals that are not related to these orbitals here. So you're going to put the electrons back in that way. And that's how you distribute them here. You're trying to move electrons between S and P, and that's not what's happening. It's like the analogy is like the $5 bill and the three $1 bills. You exchange it for four $2 bills, and they're being distributed differently than they were originally. A $5 bill and three $1 bills. Like if you had to distribute that to four people, you would exchange it for four $2 bills, and you distribute them across equally, right? That's what hybridization is. In this one, what's happening here is that one person is getting, like, so here you only have three people, but one person's getting twice as much share with those $8, right? So if you had $8 and you had a $5 bill and three $1 bills, you'd only need to exchange six of those dollars so that everyone got their right share, right? You see what I'm saying? So like, okay, because you're, okay, what is your thought here so I can fix it? Because you're trying to make things more complicated than they need to be. Redistributing them. No, you make an sp2 orbital because those three orbitals I circled make three brand new orbitals that are different than the original three orbitals that we had here. Do you see how that they're on a different energy level than the original ones I drew? Yeah, I've drawn them vertically like this, Juan Diego. Low energy, high energy. These three lines are in between that energy. That's what hybridization does. It mixes the energy orbitals to make them of a lower energy than this one, but higher energy than this, so they're all the same. Because you need a double bond in this structure. The example I'm giving you here requires a double bond, so this electron is in this p orbital to allow double bonding right here. Unless you have a lone pair in there, no. You can have two electrons in sp hybridized orbital, but that means it's a lone pair. Like, if you're bonding with something else, you're each sharing one electron, right, Juan Diego? So if you're trying to make this carbon ready for bonding, you want one electron in each bond. If you had extra electrons, then you would have lone pairs, and then you'd have two electrons in there. But right now for carbon, you don't need that because you're having all bonds. Lone pairs are when you have two electrons in a hybrid orbital. That's what that is. So what you're asking about is why don't you double it up? Because you only double up hybrid orbitals if it's a lone pair. That's the only time you do it. You'll never have two electrons in a orbital that needs to be bonded. Nick, Arda, and then Joey. No, no. You all have to draw out the X and Y and Z axis and stuff like that. Yeah, because it serves a purpose to show that it's like a ring around the entire thing. Yes, it would be Y shape. Yes, right, Nick. Arda. It's not more stable. It takes more energy to break because you're breaking two bonds versus one. But itself, the second bond itself is actually less stable, which is why it takes less energy to break a double. Like it's not double a single bond to break a double bond. It's actually less than a double a single bond. Um, sorry, Joey, and then Azzy. Yes, 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 correct. Yeah, Azzy. A double bond contains a sigma bond and a pi bond. That's what. No, not yet. Oh, yeah. So when you have a pi bond, you need an unhybridized p orbital. So that thing I circled there, that's the unhybridized p orbital that allows a double bond to occur with the oxygen in the molecule. So if I ask you what's the hybridization of this carbon, it's sp2 because you only need to hybridize three orbitals to form all the single bonds and lone pairs that you need. because the extra p is in the pi bond, so you don't count that in hybridization. Correct. Yes, correct. Yes, the first bond's sigma. The second bond is that up and down parallel that we drew. Yeah, that's this. So like this double bond right here, azine is like this. That's what it's illustrating. Yes, yes, the blue that I colored up there. That's the only way you can have a double bond. Yes, yes, correct. Exactly. The pi bond itself is more ready to react because the electrons are constantly moving kind of back and forth, and they're able to bond with other things very easily. Yes, they are further out as well. Yeah. Timur. Yeah. You need to focus on. You need to include the lone pairs though too. So like the thing is, like if you have something like NH3, okay, and I want the hybridization for N. It has how many sigma bonds? Three sigma bonds. And how many lone pairs does it have? One. So it needs a total of four hybrid orbitals. So it's sp3. That's what I was telling you earlier. Because you're like, well, you want me to draw it? Like, no, you don't need to draw it. You're just looking at the Lewis structure. It's sp1. Correct. Yes. Yes, Joey. Yes, you can associate with the electron domain geometry. So this relates to the electron geometry. In fact, if you want to put it on your chart, sp3 with four hybrid orbitals relates to tetrahedral. So if you have sp3 hybridization with four regions of bonds and lone pairs, that's tetrahedral. Guess what trigonal planar is? sp2. Guess what linear is? sp1. Now, the problem is, oh, sorry, I'll let y'all write that down. So these hybridizations go with the electron geometries as well. Yes, but it's not that bad. So the thing is, and this is what I think Nick was asking earlier about, like, or someone was asking about expanded octet. Expanded octet can only happen on row 3 and down because you need a certain sublevel to allow for expanded octet to occur. You need the D sublevel, which only happens in row 3 and down. So what happens here is that to get 5 orbitals to hybridize, what are you going to use? Well, no, S, 3 Ps, and then 1 D. So you take the extra, like, so there's only 3 maximum P orbitals you can use. So you take an empty D orbital as your fifth. So this is sp3d1. Yep. So if you want to think of it this way, if you want to list out all your available orbitals, it'll be like this. And whatever number of hybrid orbitals you need, just start counting from left to right, and that's what your hybridization is. Yes. With how many bonds and lone pairs it has. So for example, Jada, if you look at this, and I tell you I have, I don't know, three sigma bonds and 2 lone pairs. How many hybrid orbitals do I need? 3? Yes. 5. So what would my hybridization be? Yes. Okay. Yeah. No, there's only 3 p orbitals. There's P can hold 6 electrons as Dean, but only 3 orbitals. That's why you have to use the d orbitals for expanded octet. Sol. Mm-hmm. Yes. Yes. Yep. Just keep going from left to right. Wait, sorry, say it again. I don't know what you just said. I'm sorry, say it again. No, wait, how's that five? Is how many? Okay, hold on. S is one orbital. How many p orbitals are there? So how many orbitals is that? That's not what you said earlier. So yes, d is five. Yes, that's not what you said earlier. I swear. Why are you? No, no. Oh, no. Don't put the CLs into every single individual orbital. One ego. Like you're mixing. Like I never told you to do that. Like if I said that anytime, then I was wrong. But you're fill. No, no, no. Okay. Here's the thing. Okay. The way hybridization works. Okay, is you've got to make every atom kind of on an equal term so that when they bond, they all get treated the same. Okay, so if four things are bonding, you need to make sure they're all being treated the same. They have the same orbital to bond with. So you make your orbitals change so that they're all the same. Yes. Yes. So you have to ask yourself, how many single bonds and how many lone pairs do I have? And that's how many spaces I need to make. That's how many hybrid orbitals I need to make. And that's what my hybridization is. That's what you want to focus on. Are you going to have to explain it in detail? No. Well, okay. Okay, but if I have four bonds and two lone pairs, it's still six. No, I'm just giving you another example because you were just saying only bonds, but if you had three bonds and three lone pairs, that's still six. Four sigma bonds and two lone pairs. Yes. But stop saying bonds though, because lone pairs count in that too. I just don't want you memorizing that because then when you have a lone pair, you'll forget to count it. Yes, sigma bonds and lone pairs, not pi bonds. So only sigma bonds and lone pairs. So the first bond between each atom and lone pairs, that's it. This may reside. Correct. Yeah, correct. Yeah. Yes. No, it'd be probably unhybridized p orbitals still. Yes. Yeah. Okay. Well, one more thing. Okay. As Ian was asking, just to make sure we understand, okay, a triple bond is one sigma bond and two pi bonds. So you can never have more than one sigma bond in any type of bond you have. So even if you have a triple bond, you still count that as one sigma bond for hybridization purposes. Okay. So your job is look at a Lewis structure, count up the sigma bonds, and count up the lone pairs. That tells you your hybridization every time. Sigma bonds and lone pairs. Ignore pi bonds altogether when you're trying to figure out hybridization. That's all I'm trying to tell you. Yes, Joey. Yes. One pi bond. No, but when you do hybridization, you don't distribute you pick one structure to do it on. Okay. Pi, yes, correct. You always start with one sigma bond and you always just add pi bonds. Yes, Sol. Correct. Yes. Oh my goodness, we're going over. Okay. Formal charge really quickly. Okay. Sorry, we're going over, but I'm just gonna do this. Formal charge is used to determine the optimal structure of a Lewis structure. because sometimes you have more than one place you can put a double bond, and that affects the shape or affects the Lewis electron distribution, and you have to figure out which one's the ideal state of it. So you calculate formal charge of an atom as the valence electrons it has minus the bonding electrons minus the lone electrons. Not lone pairs, but lone electrons. So a lone pair is two. Correct. Yes, correct. So a lone pair is two lone electrons. Yes. Yes. Well, in a bond, you only contribute one bonding electron. So a bond could be, you could write it as a bond as well. I was just writing everything in terms of electrons, but you could do this as bonds as well. So here's how this works. Let's pretend we have something like SCN minus. Well, what happens is SCN can actually be drawn three possible ways, and it fulfills all the Lewis structure requirements. And test structure, everything, it fits. All these are technically correct, but one of them is the best structure. And you want to look at two things. You want to look at one, formal charges closest to zero. Okay. If a tie charge, let me rephrase this. If there's a tie, the negative charge goes to most electronegative. Oh, I'm running out of space here. Most electronegative atom. So like, for example, in a molecule, if you have like a -1 formal charge somewhere and you have to put it on an atom, you always put it on the atom with the most electronegativity, the highest electronegativity. So if we're doing this here and we're calculating this, S has 6 valence electrons in everyone, carbon has 4, nitrogen has 5. S here has 2 bonds and 4 electrons, 4 lone electrons, which is 0. Here it has 3 bonds and 2 lone electrons, so it's 1 plus. Here it's 1 bond and 6 electrons, so it's 1 minus. In charge, remember, sign goes last. Carbon is 0 in all of these. Nitrogen is 1 minus, 2 minus, and 0 here. So of these 3 choices, which one can we eliminate right away? Which ones are not close to the 0? The second one. Notice the values are not as close to 0 as possible. 0, 0, -1, or 1 negative is closer than 1 plus, 0, and 2 minus. So you have to choose between this choice and this choice. Sorry, let me not circle this, but. So what's the difference between these two structures? Which one is 1 minus? Correct. Okay, so you either have it on S or N. Well, N is more electronegative than S, so it ends up being that, and we can see electronegativity on the data booklet. There's a whole data table for electronegativity here, and you can see that N is 3.0, S is 2.6. So if that's the case, N gets the 1 minus, and your best structure is this structure of the three. So calculating formal charge comes down to that. Valence electrons minus bonds minus lone electrons gets you a value. And I've seen them do a table like this on a data on the short answer. Like they literally have a table and have you calculate all the formal charges for the possible structures. Yes, Jada. Yes. So you see how there's a 1 minus on both structures, like A and C. But the 1 minus on the right one is on the S, and the 1 minus on the N is here. Correct. So N is more electronegative, so that gets the priority. Correct. N wins. Yes. They should all add to -1. Yes. They better. Because they should be correct structures, right? I see what you're saying. It's the range of values that you have needs to be as small as possible. So +1 to -2 or 2 negative is wider range than 0 to 1 negative. Because I know what you're saying. I think you just realized that they should all have -1 negative, or you did something wrong because the molecule is 1 negative charge. Yes, Joey. Yes, correct. So if your sum of your formal charges does not add up to your overall charge, then you did something wrong. So that's to reinforce what Azim was asking about, is that your sum of your formal charges should add up to 1 negative here because the overall charge is 1 negative. Oh, one, you can use your data booklet to look it up because they actually have the values in the data booklet. N is higher than S, but it does go up toward F. F is the most electronegative element, so N is closer to F, and so it has a higher electronegativity. Yes. For the short answer, yes. So guess what they're going to ask you on the multiple choice? You get the normal one. You don't get all of them. Correct. You don't get the electronegativity one. You just get a plain one that you're used to seeing on tests and stuff like that. Joey, and then I'm on. For what? Yeah, you just ignore lone pairs. No, you do. They're just not drawn in structural formulas. But they'll probably ask you to draw the Lewis structure for their organic molecule if they want to do formal charge. They're implied to be there. I'm on, and then Sarah. Yeah, sure. Sarah, what's up? Yes, this is the end of the notes. Okay. Okay. I'm gonna stop recording right now so I can upload it. I'm not gonna edit out me getting mad at Juan Diego.